Hi, this is Rich. We're at the SCALGO booth at ILMF 2012 in Denver, and we're here with Thomas Moelhave, the CTO of SCALGO, which was a result of a decade's worth of research at Duke University in the computer science department. And he's here to show us about a couple of their products that they've got called SCALGO Hydrology, SCALGO Model, and a service they offer called SCALGO Flash Flood Modeling. I'll hand it over to you.
So yes, we have two products besides the software product, SCALGO Hydrology and SCALGO Model. And Hydrology does basic hydrological modeling, flow accumulation, flow directions, watersheds, that kind of stuff. SCALGO Model takes LiDAR point clouds or other kinds of point clouds and produces models, triangulations, rasters, and also does some other computation on them. So what sets us apart is we can run on very large data sets. That's what all the research is about. As an example, I'll show you, we have the shuttle radar topography mission from NASA, which is a giant raster, global raster. It's about 60 billion cells, including the later cells. And here we have flow accumulation for the entire SRTM model. And this is computed in one go on a standard desktop computer with 4 gigabytes of memory on the computer, and it took about 2 days. You just push a button and you let it run, and then you get this.
This is the 60 billion?
This is the 60 billion. Excuse me, it took a day and a half on a standard computer with 4 gigabytes of memory. And then you can play with it. This is just a visualization. This is not the actual software product, this is just visualizing the output. You can play with the rivers and see. We have also computed worldwide watersheds, again just in one go on the big data set. So this allows you to run on something like this, but it also allows you to run on very smaller but much more high resolution models. So for instance, we have the entire country of Denmark, and we've computed various things. For instance, what happens when the sea levels rise, what part of the land is flooded. This is computed on a 1.6 meter nationwide model, and again it takes up a couple of thousand tiles on disk and hundreds of gigabytes, and it takes a day and a half to run this simulations on the entire country. So those are our software products. They run in a standalone graphical user interface, but they also come with an ArcGIS extension, so you can run them from your ArcGIS toolbox or from the model builder. We also have a service which we call the flash flood mapping, which is a more sophisticated hydrological analysis tool. And I'll show you one example here. It deals with what happens when it rains a lot all of a sudden and water accumulates into depressions. Depressions slowly fill up, eventually they'll spill over, and watersheds will merge, and water will now go down to downstream depressions from the depressions that fills. So let's zoom in on a random region here. You can see all these little blue spots are things that are underwater, given, in this case, 35 millimeters of rain. So we can treat the water level, and we'll see these depressions under more and more water.
So you have to model the entire watershed?
Yes, yes. Yeah, so you want to do this on a high-resolution model, so you get an accurate result, but you can also want a large extent, so we can get all the interactions there. Because when one watershed is, one depression is full and watersheds merge, that water goes down to the next one downstream. So you need to have multiple watersheds next to each other. And if you enable a satellite view, you can see that so this image is of course completely independent from the computation itself by Google. But if you look at, for instance, here, you can see that it actually matches with where you can see on a satellite photo where water is usually standing. And
you can see the darkness.
Fields, yeah, exactly, the patches in the grass. So it's very good modeling, and you can use it in cities as well. If you move to another area, this is the last example. We went to a conference here last year. This is sort of on a slope. This is the conference center was around here, so we did a computation of that area. Since we know how much water is standing in the depressions, we can compute the river network at that time, given any amount of water. So 50 millimeters of water, for instance, you get something like this. Red means there's a lot of water flowing, green is a little less water. There's a watershed here, water flows downstream. This is a high-resolution model, so you can see how the water follows the streets. And there's another watershed that sits here and follow down into the sky. Now as it rains more and more, now I'm going to turn the rain up.
So you circulate.
This area here. This thing grows, eventually it stops growing because it's full. And what happened, if we look at how the river network looks after 100 millimeters of rain, is that now this is full and the water that used to go here now goes down the stream a little more and then merges with this guy. So now this guy...
So the street becomes the flow, and that's when you get this.
Yeah, you get flash floods. Yeah, exactly. So this is the sort of analysis you can do. You need to be concerned about the interactions. You need to make sure that you know that when you're here that you can get all the water from here as well. So that was a short overview of some of our products.
Great. Well, thanks, Thomas, and it's a pleasure, and thanks for your time.